There we go. Hello, Rails World. My name is Peter. I'm on the Ruby core team, and I'm a senior developer at Shopify on the Ruby infrastructure team. In this talk, I'll be talking about configuration and tuning you can do to optimize the Ruby's garbage collector for your Rails app. You can find these slides at this URL or at this QR code. Don't worry, I'll leave this URL up for a few slides. First, I'll talk a little bit about what a garbage collector is. Contrary to the name, garbage collectors are not just responsible for reclaiming data objects. They're responsible for the whole life cycle of objects. Garbage collectors are responsible for allocating memory when the object is first created and recycling that memory when the object dies. Garbage collectors are responsible for determining when an object is no longer alive by keeping track of lifetimes of objects. There are various techniques to do this, such as reference counting or marking. Ruby uses a marking garbage collector, and we'll see what that means later on in this talk. And as you know, Ruby is a garbage collected language, which means that you don't have to allocate memory when you create objects and free that memory when you're done using the object. Let's take a closer look at what Ruby objects are under the hood. Every Ruby object lives in this thing called a slot, which is a region of memory allocated for the object. And these slots are acquired from the garbage collector. And we'll soon see how these allocations happen. These slots are of a fixed size and cannot be resized. And sometimes we need to allocate more memory than what the slot offers, in which case we'll allocate the memory externally, such as through the system using malloc. The garbage collector doesn't allocate slots individually from the system. These slots live in heap pages. Allocating each slot individually from the system would be bad for performance, so we allocate in units of heap pages. In Ruby, heap pages are 64 kilobytes in size, and all slots in the page are of the same size. This is done for simplicity and to avoid external fragmentation. External fragmentation is when allocation of small-sized objects in between of large-sized objects causes small gaps that can no longer be reused by larger objects when these small objects are reclaimed, which increases memory usage. Ruby 3.2 introduced a new feature in Ruby called variable width allocation, which allowed the allocation of dynamic-sized objects through the garbage collector. Prior to this feature, all slots were 40 bytes in size, which caused objects that needed more memory to have to allocate it externally. This was bad for memory efficiency and bad for performance. Variable width allocation enabled dynamic-sized allocations through the garbage collector and introduced this new concept called size pools. Every size pool holds a collection of pages, and every page in a size pool contains the same slot size. There are currently 5 size pools in Ruby with slot sizes 40, 80, 160, 320, and 640 bytes. These numbers were chosen for the best memory efficiency and performance. Let's recap the data structures we've discussed so far. We have a slot, which is used to hold data for a single object. And these slots live in pages. And there are many pages in the system, each with varying slot sizes. And pages with the same slot size live in the same size pool. 4 size pools are illustrated here due to slide space constraints, but there's actually 5 size pools in Ruby. We've just seen the data structures inside of the garbage collector. Now let's talk about how these objects are actually allocated. Each heap page holds a linked list of slots that are empty called the free list. And to allocate an object, we simply pop an element from the linked list to allocate the object into. Here's an illustration about how object allocation works. Here's a heap page with a few objects allocated. And we have a free list that links all of the free slots on this page. And let's try to allocate this new object that is a regex. And we allocate this object at the head of the free list, and we move the free list to the next element. And we can keep on allocating objects until we run out of free slots. And at this point, if we don't have any more pages with a free list, then we must either allocate a new page or run a garbage collection cycle to free up slots. Let's take a look at what happens when Ruby's garbage collector runs. Ruby uses a mark and sweep garbage collector, which, as the name implies, has 2 phases. In the mark phase, we traverse the object graph and mark the objects that we traverse. And in the sweeping phase, all of the unmarked objects are dead and can be reclaimed by the garbage collector. There's technically a phase in between of marking and sweeping called the compaction phase. However, it's important to note that compaction is not enabled by default. If enabled, compaction moves objects around in the Ruby heap to reduce fragmentation. This can reduce memory usage and increase runtime performance. It's important to note that Ruby uses what's called a stop-the-world garbage collector, which means that all execution of Ruby code is paused while the garbage collector runs. This simplifies the implementation, avoids the need to perform synchronization, and avoids the possibility of race conditions. However, the longer the garbage collector takes to run, the longer the pause in your application. In the Rails app, if this happens during a request, then your request could take much longer than usual. We start the garbage collection cycle with the marking phase. This is the phase where we determine which objects are alive by traversing the object graph by reading the references of objects using a breadth-first traversal algorithm. For example, for an array, the references will be the contents of the array. For a hash, the references will be the keys and the values of the hash, and for an object, the references will be the instance variables of the object. Ruby uses 3 colors to mark objects. All objects are initially white, which means that the object is unmarked. When we mark an object, we color it as gray. This means that the object has been marked, but the references have not yet been traversed. Remember, we're using a breadth-first traversal algorithm, so we do not immediately inspect the references of the objects that we mark. Later on, after we traverse the references of the gray objects, we mark it as black. And at the end of the marking phase, all of the unmarked objects are no longer reachable and can be reclaimed by the garbage collector. Here's an example of a Ruby heap with several objects. Object references here are shown using arrows. For example, object A refers to object F, which refers to object I. We start marking from the root objects, which include objects on the stack, global variables, and top-level constants. We color the references of the root objects as gray, since we visited them but have not yet visited their references. We then visit a gray object, and let's pick object A here, and visit its references. This colors object A as black, and we traverse the one reference object F, and we color it as gray. And we repeat for the next gray object, object B. Object B has 2 references, object G and object H, so we color both of these objects as gray. We now inspect object C, which has only one reference, object H, which is already marked gray, so we do nothing. We then inspect object F, which has one reference, object I, and then object G, and then object H, and finally object I. Now that we have no more gray reference, every object that is colored black is a live object, and every object that is white is dead and can be reclaimed by the garbage collector. We can see here that object D and object E were never traversed, therefore they are dead objects and will be reclaimed during the sweeping phase. Now I'm going to add some more complexity to the marking phase. Ruby uses what's called a generational garbage collector. And generational garbage collectors are based on the generational hypothesis, which states that objects either live for a very long time and are basically immortal, or live for a very short period of time. In a Rails app, most objects created at boot are basically immortal. These are things like your classes, your constants, and your database connections. During requests, the objects that you create usually only live for as long as the request. These are things like your active model objects, your logging entries, and other objects to help serve the request. Your Rails app basically doesn't have anything that lives for a medium amount of time. Everything is either immortal or lives for a very short amount of time. In a generational garbage collector, newly created objects are placed in the young generation. And objects that survive for a while, and in Ruby it's 3 garbage collection cycles, they get promoted to the old generation. We take advantage of the generations by splitting marking into 2 types. Minor garbage collection cycles marks only young objects and assumes that all of the old objects are already marked. This can make garbage collection cycles much faster because of the significantly fewer objects that get marked. And because of the generational hypothesis, we should be able to reclaim a large portion of the objects allocated since the last garbage collection cycle. But sometimes we still need to mark all of the objects in order to reclaim some old objects. And this is called a major garbage collection cycle, where we mark both the young and the old objects. However, major garbage collection cycles can often take as much as 10 or 20 times longer than a minor garbage collection cycle, so it should be avoided in a Rails app. Let's take a look at an example of a minor garbage collection cycle using the same heap but with generation. Some of the objects here are young and some of the objects here are old. Remember, in the minor garbage collection cycle, we assume that all old objects are marked. So we start by marking all of the old objects as black. Note here that object E is a dead object, but it is marked because it is an old object. So we won't be able to reclaim it in this minor garbage collection cycle, even though it is a dead object. So then we mark like usual, starting from the root objects. We start, from the root objects. And we mark all of the root objects as gray, and we traverse the references of object A. But since object F is an old object, it's already marked black, so it is not inspected. We then traverse the references of object B, which is object G, and object H. And then finally, we color object G black. In this minor garbage collection cycle, we marked 3 young objects and skipped over 4 old objects. This significantly reduced the number of objects marked, which should improve performance. However, the only white object left here is object D, so later during sweeping, we can only reclaim object D. Object E here is an old object, so we'll need to run a major garbage collection cycle in order to reclaim it. I just showed you how Ruby's garbage collector takes advantage of generations to implement minor garbage collection cycles. But I left out a few critical implementation details. During runtime, we can add a reference from an old object to a young object. But old objects are not traversed during minor garbage collection cycles, so the young object will not be marked, and so it will remain white all throughout marking. So then it will appear to be dead by the garbage collector. And this will be a terrible bug, because the old object will now refer to a reclaimed object. And if we try to read that young object, then we'll either crash or get a completely different object. This is solved using write barriers. Write barriers are callbacks to let the garbage collector know when a reference is added from one object to another. For references to objects of the same age, the write barrier does nothing. And for references from old objects to young objects, the write barrier places the old object on the remember set. The remember set is a set of objects that is traversed during every minor garbage collection cycle. However, write barriers are not required, and there are some types in Ruby and some native extensions that do not support write barriers. Types that support write barriers are called write barrier protected, and the types that don't support write barriers are called write barrier unprotected. So what do we do about write barrier unprotected objects? They don't support write barriers, so we won't know when a reference is added to a write barrier unprotected object. This is solved by always placing the write barrier unprotected object in the remember set. Since objects in the remember set is marked in every minor garbage collection cycle, we lose the benefits of generational garbage collector for write barrier unprotected objects. Let's take a look at an example where we have an old object here that refers to a young object and a write barrier unprotected object. Note that the write barrier unprotected object doesn't have an age because it is neither old nor young because it does not participate in the generational garbage collector. So we now introduce the remember set, which is part of the list of root objects. The write barrier would add object F to the remember set due to the reference to the young object, and the write barrier unprotected object will always be in the remember set. In a minor garbage collection cycle, we first color every old object as black. However, every object reference from the remember set would be colored gray, so we can inspect every reference. We then mark like usual, where we pick a gray reference and mark the references as gray. Let's pick object F here. We then mark object H, and then object I, and finally object J. We've just seen how the marking phase in Ruby's garbage collector works. And so now we've determined the liveliness of every object in the garbage collector. And so now all unmarked objects are dead. And the sweeping phase reclaims the resources of these dead objects. In addition to reclaiming the slot for the dead object, we also reclaim any externally allocated resources, such as closing file descriptors, closing sockets, or terminating threads. Here's an example of the sweeping phase using an example with 2 heap pages. Marked objects here are shown in black, and unmarked objects are shown in white. We sweep by inspecting one object at a time. We first inspect object A, but since it is a marked object, we skip it and do nothing. Object B here is not marked, so we reclaim it, and now we're left with an empty slot that we can allocate a new object into. Our next slot is not marked, but it is an empty slot, so we skip it and do nothing. And we can keep repeating this for the rest of the slots on this page, where we skip marked and empty slots and reclaim unmarked slots. And after we're done with sweeping this page, we'll move on to the next page and sweep the next page. The compaction phase in Ruby's garbage collector reduces fragmentation in the Ruby heap. It moves objects so that all live objects are adjacent to one another. This can decrease memory usage and improve performance. It can save memory because there will be more completely empty heap pages, which can be released back to the system by the garbage collector. If you're using a forking web server such as Unicorn or Puma, then this can reduce the amount of copy on write, which can decrease the amount of memory used by your Rails app. It can also improve runtime performance through better CPU cache locality, and can also speed up garbage collection cycles. Variable width allocation takes advantage of compaction by moving objects to their optimal size. Objects can change size during runtime, and this can help further decrease memory usage and improve runtime performance. It's important to note that compaction is not enabled by default. To manually run compaction, call gc.compact or set gc.autocompact to true. Autocompaction runs on every major garbage collection cycle. I didn't have time to give an example about how compaction works, but that was a quick introduction to how the garbage collector works in Ruby. If you want a more in-depth article about how the garbage collector works with examples, check out my blog post at this link. Now that we've seen how the garbage collector works from the inside, let's apply this knowledge and see how we can collect metrics from the garbage collector. This will help us gain insights into our Rails app and find ways to optimize performance. The method to get basic statistics from the garbage collector is gc.stat. It gives us information such as the total number of garbage collection cycles ran. We want to minimize this number, as more garbage collection cycles means more and possibly longer pauses during requests. And we certainly don't want to run more than one garbage collection cycle per request, since very little objects will be dead during a request. So the additional garbage collection cycles will not be doing much. We also see the total time in milliseconds spent inside of the garbage collector. Using this information, you can determine the proportion of time spent inside of the garbage collector per request. If this proportion is high, then tuning the garbage collector will yield a significant performance improvement. And if this proportion is low, then tuning the garbage collector will probably not give you as much of a performance improvement. We also see the total time in milliseconds spent inside of the marking and sweeping phases. And this can help you determine which of the two phases you're spending the most amount of time in. We also see the total number of pages allocated, and the total number of pages almost directly correlates with the amount of memory used by your Rails app. However, increasing the number of pages may decrease the frequency that the garbage collector is ran. And so sometimes it's a trade-off of using more memory for better performance. We also see the number of live objects, and this is the number of objects that are currently alive, and the number of free slots, which is the number of slots that we can allocate objects into. When this number reaches 0, a garbage collection cycle is ran. However, note that the garbage collector may run due to various other reasons, not just when this number turns 0. We also see the total number of objects we've allocated since the boot up of Ruby. This can be used to determine the number of objects allocated in a particular request. If this number is too high, consider optimizing your app to allocate less objects. We also see the number of major and minor garbage collection cycles and compaction cycles. Most of the garbage collection cycles in your Rails app should be minor garbage collection cycles. And if you see that you're running majors too frequently, then it could be poorly tuned, or you could have a Ruby level memory leak. For example, if you have a buffer that holds on to logging entries, but your buffer is never flushed, then you'll have a Ruby level memory leak. We also see the number of old objects that are currently alive. Remember, the generational garbage collector segregates objects by age. And objects are young when they're first allocated and become old when they're alive for a long time. In a Rails app, old objects are usually only allocated during boot up. And so if this number continues to increase after your Rails app has booted up, then it may be poorly tuned or you may have a Ruby level memory leak. New in Ruby 3.2, gc.stat heap gives information about each size pool. There are 5 size pools in Ruby with indexes as names from 0 to 4. And the return hash contains the size pool name as the key and the statistics hash as the value. The keys of the statistics hash is the same for each size pool, so I'll just take a look at the first size pool. We see the slot size in bytes. This is the size of the slots in each of the pages in the size pool. And we also see the number of pages and the total number of slots in the size pool. Using these two numbers, we can determine the distribution of object sizes inside Ruby. And this can provide clues as to which size pools are occupying the most amount of memory in your Rails app. We also see the number of times major garbage collection cycles were forced by the size pool. And if this number is too high, then this size pool is likely undersized, and increasing the size would likely improve performance. Now that we've seen how to collect and interpret metrics from the garbage collector, let's take a look at some tuning to personalize the garbage collector for your Rails app and improve performance using the information we've gathered. This one's pretty obvious. If you allocate less objects, there's less pressure on the garbage collector, so the garbage collector runs less frequently. Less objects allocated means there's less objects to scan during marking and less objects to free during sweeping, so the garbage collector runs much faster. The strategy here is to find controllers that allocate a lot of objects and try to find optimizations to trim those allocations. If you reduce the number of times the garbage collector runs, then you should theoretically spend less time in the garbage collector. Specifically, you want to decrease the number of major garbage collection cycles, which can often take as much as 10 or 20 times longer than a minor garbage collection cycle. So how can we actually reduce the number of major garbage collection cycles? This environment variable reduces the number of garbage collection cycles at boot using the gc heap init slots environment variable. This sets the initial number of slots in the garbage collector, so the garbage collector does not need to grow the heap at boot. It will immediately be grown to that size. You can determine good values for this environment variable by measuring the number of slots in the heap after your app has reached peak performance in production. Note that if this value is too high, then your app will use significantly more memory. The Ruby GC old malloc limit and old malloc limit max environment variable determines the number of memory allocations that happen before a major garbage collection cycle gets ran. The default is 128 megabytes for the max. And at Shopify, we set this environment variable to an extremely high value to essentially turn it off. This may increase the amount of memory your app uses, but we saw a significant performance improvement. Another technique we use at Shopify is called the out-of-band garbage collector. This runs the garbage collector between requests while your Rails app is idle. Ideally, the garbage collector never has to run during a request. This technique is challenging to implement for threaded web servers, such as Puma with multiple threads. This is because we don't know what the other threads are doing, and we cannot control the other threads. Remember, Ruby's garbage collector is stop the world. So running the out-of-band garbage collector on one thread could cause the other threads to stall. We could synchronize the threads to ensure they are all not serving a request. But this would further decrease capacity, as some threads could be stalling for an indefinite amount of time to wait for a slow thread. So it's recommended to use out-of-band garbage collector only on forking web servers, such as Unicorn or Puma on clustered mode. The out-of-band garbage collector is tricky to implement, as we cannot look into the future to determine when the garbage collector will be ran. So we have to use heuristics to predict when the garbage collector will be ran. Unfortunately, if we try to run the garbage collector too frequently, then there will be long periods of stalling in between requests. And this would decrease capacity, as we would be spending time doing essentially nothing. And if we don't run the garbage collector frequently enough, then it will be ineffective, as we'll still be running the garbage collector in between requests, during requests. And as you can see, the out-of-band garbage collector is tricky to implement, but it may be worth it if you're seeing if you need to decrease response times, but you're seeing a large number of objects allocated during requests and seeing long pauses inside of the garbage collector. Let's take a look at the impacts of tuning the garbage collector on one of Shopify's highest traffic apps called Storefront Renderer. Storefront Renderer renders the home pages and product pages that buyers interact with on Shopify. So it's very important that this app has fast response times. After tuning the garbage collector, we decreased the average time spent inside of the garbage collector per request by 50%, and decreased the 99th percentile in the garbage collector per request by 80%. How does this translate to response times? Well, the average response time decreased by about 13%, and the 99th percentile response time decreased by about 25%. This is quite a significant decrease, as we spent quite an amount of time during I/O during the request, such as to the database or to caching, and this cannot be optimized by tuning the garbage collector. These performance improvements weren't just from tuning the garbage collector. We also analyzed the garbage collector and found improvements that will speed up your Rails app in Ruby 3.3. This feature adds a new configuration environment variable called the Remembered Write Barrier Unprotected Objects Limit Ratio. What a mouthful. But this calculates the limit for the number of write barrier unprotected objects that are placed in the remember set. When this limit is reached, a major garbage collection cycle is started. Previously, this limit was calculated as twice the number of write barrier unprotected objects that exist after a garbage collection cycle. However, if very few of them survive, then this limit is very low, so major garbage collection cycles are triggered very frequently. This limit is now calculated as a proportion of the amount of old objects and defaults to 1%. On Storefront Renderer, this feature improved average time in the garbage collector by about 33% and halved our 99th percentile time in the garbage collector. This translated to a 4% decrease in average response times and a 14% decrease in 99th percentile response times. The next feature changed the garbage collector algorithm for references from old objects to young objects. In the old algorithm, we immediately promoted the young object to the old generation. But this created many old objects during requests, because we sometimes store temporary objects in old objects. For example, temporary objects are placed in the buffer during logging. But if the buffer lives for a long time, then it's likely an old object, but the buffer gets flushed frequently. So it doesn't make sense to make the entries also old generation. The new algorithm places the old parent object in the remember set when a reference to a young object is added. This allows the young object to age like usual and only be promoted to the old generation after it survives for a long time. This improved our average response time, our average time in the garbage collector by 19% and our 99th percentile time in the garbage collector by 12%. This translates to a 4% decrease in average response times and an 8% decrease in 99th percentile response times. You can learn more about these two features coming in Ruby 3.3 in this blog post, where I discuss how these features work and the impacts in greater detail. There's quite a lot of things I talked about in this talk, from a crash course on how the garbage collector works, to how to collect metrics from the garbage collector, to some ways to tune the garbage collector, to some new garbage collector features coming in Ruby 3.3. You might have gotten it, or I might have left you more confused. But I have good news. You can forget it all. Today, I'm announcing the Autotuner gem. You're among the first people in the world to hear about this. This is a gem I've been working on in the past few months. This gem analyzes the garbage collector between requests and provides suggestions to tune the garbage collector for your app. You can find the source code of this gem at github.com/shopify/autotuner. Setting up this gem is extremely simple. Follow these two simple steps in the README, and it will begin emitting garbage collector tuning suggestions. After you set it up, you'll get tuning suggestions that look like this, which first explains what the tuning suggestion attempts to solve and the impacts on your app. This tuning suggestion reduces the number of minor garbage collection cycles, which may improve response times, but may increase memory usage. And then it gives the environment variables to apply this change. And then advice about using A/B testing to compare the impacts of this change. I'll now talk about how we experiment and compare impacts of garbage collector tuning at Shopify. Initially, all of our servers are untuned, meaning there's no tuning applied. After Autotuner gives a suggestion, we designate a small random portion of servers as the experimental group. If your app is high traffic, this might be around 5%. If your app is low traffic, this might be around something like 30%. The idea is to keep the group small in the unlikely event that the tuning causes a significant degradation in performance. However, big enough to compare the results while keeping variance low. We apply a tuning to the experimental group and compare the impacts of this change to the untuned group. Response times fluctuate significantly depending on the type of the request, the load of your web servers, and external factors such as the response times of the database. So it's difficult to measure the impact of tuning over two separate time intervals. It's much easier and gives us more confidence to compare the performance impact over the same time period. If tuning provided a positive impact on performance, then we create a stable tuning group that is similar to the experimental group in size, but only contains tuning that have yielded a positive performance impact. We copy this tuning over and apply it to both groups. We then apply the next tuning suggestion to the experimental group, and we compare the impacts of tuning to the stable group. And if this tuning doesn't provide a positive performance impact or gives a trade-off that you don't want, then we can remove it. Sometimes tuning may give a trade-off that you don't want. The most common one being better average response times, but making extremes like 99th or 99.9th percentile worse. We can keep experimenting with new tuning suggestions one by one in the experimental group. And we keep suggestions that have a positive performance impact by copying it over to the stable group and remove ones that do not give a positive performance impact. Once we're satisfied with the results of tuning, we can compare the total impact of tuning to the untuned group. And once we've gathered enough data, it's finally time to roll out tuning to all of the servers. And if everything has gone right, you should observe a performance improvement. You can find the slides for this talk at this QR code. Please check out this gem at this GitHub URL. Feel free to reach out to me through Twitter. My handle is Peter Zhu 2118, or through Mastodon on ruby.social, or through email. My email is peter@peterzhu.ca. You can always ask me questions today during the conference. Thank you very much for listening to my talk.